right away. Right away. We're getting right into it. Refrigeration. Oh, random page. Here we go. Okay. A lot of reading here. The system adjusts the intervals between defrost cycles to be short enough to maintain a clean coil, but not so short that energy is wasted performing unnecessary defrosts. As humidity changes, as humidity conditions change and the defrost load increases or decreases, the system adjusts the cumulative runtime to match the change in the frost load. Hot gas defrost. A defrost system that is seen less frequently in domestic appliances is the hot gas defrost system. This type of defrost system redirects hot compressed vapor from the compressor through the evaporator to defrost it. Hot gas defrost systems are more commonly used in commercial ice machines to aid the harvest process. When hot gas defrost is used in a domestic refrigerator or freezer, the system includes a bypass line that connects the compressor discharge line to the evaporator inlet. A solenoid-operated bypass valve is installed in this line. During normal operation of the system, the valve remains closed. When the defrost timer triggers the defrost cycle, the valve opens and hot gas enters the evaporator at a point just after the capillary tube inlet. The hot gas thaws the frost from the inside. One concern with this type of system is that it adds a component to the basic refrigeration system, and any added components are potential sources of system failures and increase the cost of the unit. So I'm just looking at this figure 1819. This solenoid valve operates as a defrost bypass by opening a passage between a compressor's discharge line and an evaporator. Check with the solenoid valve's manufacturer to ensure it is installed in an acceptable position for proper operation. Okay. In a refrigerator or freezer equipped with a hot gas defrost system, two solenoid valves in the refrigerant circuit open and close to provide either the refrigerating cycle or the defrost cycle. During the refrigerating cycle, as shown in the figure, the solenoid valve in the liquid line is open and the solenoid valve in the bypass line is closed. When the valves are in these positions, the refrigerator operates normally. During the defrost cycle, the solenoid valve in the liquid line closes and the solenoid valve in the bypass line opens. Since the solenoid valve in the liquid line is closed, no liquid refrigerant is flowing through the metering device into the evaporator. Since the solenoid valve in the bypass line is open, hot compressed refrigerant vapor flows through it directly into the evaporator. It passes through the evaporator, through the accumulator, and back through the suction line to the suction side of the compressor. As it passes through the evaporator, the hot vapor melts the ice from the evaporator surface. The vaporized refrigerant picks up some heat as it passes through the suction line. As it passes through the compressor, the heat of compression raises the temperature of the refrigerant enough that it continues to heat the evaporator and remove the frost. Little or no condensation of vaporized refrigerant takes place during this cycle. Semi-automatic defrost. Some domestic refrigerators use semi-automatic defrost systems. These systems defrost the unit when the user presses the button on a defrost switch, and then return the unit to regular operation automatically after the unit has defrosted. A second type of semi-automatic defrost system raises the operating temperature of the evaporator a fixed amount when a defrost switch is pressed by the user. When the defrost operation is triggered, the evaporator temperature becomes warm enough to cause defrosting while still providing satisfactory refrigeration. Pulling on the switch returns the system to regular operation. Refrigerators with semi-automatic defrost systems frequently use a motor control with two sensing elements. One sensing element controls the compressor motor during the normal refrigeration cycle by using pressure within a gas-charged sealed capillary tube. As the temperature in the refrigerated space rises, the gas within the capillary tube expands and pushes on a diaphragm, which in turn closes on a set of electrical contacts, starting the compressor motor. Okay, random page. In an open-loop cooling tower, the water from the condenser flows into the cooling tower and over the wet decks and filled directly. This water is then recirculated through the condenser before returning to the cooling tower. The condenser and cooling tower share the same water. In open-loop circuits, some of the water will be lost to evaporation, drafts, or draining. In a closed-loop cooling tower, the water in the condenser carries its absorbed heat into a heat exchanger that passes the heat into a separate stream of water that flows through the cooling tower. This separate cooling tower water flows over the wet decks and fill to release the heat from the system. Condenser water and cooling tower water are separate and exclusive. They never mix or contact each other. Condenser water remains in a single circuit consisting of the condenser and one part of the heat exchanger. Cooling tower water remains in a single circuit consisting of the cooling tower and the other part of the heat exchanger. A closed-loop circuit allows far fewer contaminants into the condenser water loop than an open-loop circuit. In a closed-loop system, condenser tube cleaning can be performed much less frequently than in an open-loop system. Cooling tower airflow designs. Cooling towers can have one of two different airflow designs. In a counterflow cooling tower, air and water travel in opposite directions. Air enters from the lower part of the tower and flows upward to exit at the top. Water enters from above and drops downward to the sump or cold water basin. In a cross-flow cooling tower, air flows across the wet deck from side to side. While water drops downward from above, the air and water cross each other's path. Cross-flow cooling towers can often be identified as using entire sidewalls as air inlets. Ruptured disc valve bodies generally have a threaded port for permanently installing a pressure gauge. The gauge port is sealed off from the system pressure unless the disc ruptures. If the gauge displays high pressure, the ruptured disc has burst and must be replaced. Ruptured discs are typically installed between a system and a spring-loaded relief valve. The ruptured disc blocks refrigerant from reaching the relief valve under normal operating conditions. This eliminates the possibility of small amounts of refrigerant leaking through the relief valve during normal system operation. However, if the system pressure exceeds the maximum allowable limit, the ruptured disc bursts to expose the relief valve to system pressure. The spring-loaded relief valve will then vent refrigerant to bring the system pressure back into the allowable range and will reseal once the pressure has been reduced. Some manufacturers have integrated rupture discs into their spring-loaded relief valves to prevent potential leakage at the valve seat. These relief valves also contain a filter trap that collects the fragments of the disc if it ruptures. Mufflers. Compressor pressure pulses are noisy and travel through refrigerant lines. Mufflers are used to reduce the noise from pressure pulses. Okay, there's 3 pages. Thank you for tuning in. I will see you soon.